Welcome to the deep dive. Today we're looking into something pretty critical. The physical limits hitting AI clusters and, well, the biggest data centers out there. You've probably heard about the memory wall, right? That gap between processors and memory. Well, now, with GPUs needing to talk to each other constantly, we're smashing into what our sources are calling the networking wall.
Yeah, it's a really fundamental problem.
At its heart, it seems to be this unavoidable trade-off. Data center designers face this triangle: link reach, power use, and reliability. The catch: you only get to pick two.
Exactly. Want reach and low power.
Right.
Reliability suffers. Want reliability and low power. Well, then your reach is tiny.
And it's not just annoying, it's actually holding back how big and fast we can build these next-gen systems. But the research we're diving into today outlines something pretty radical from Microsoft Research. It's called Mosaic.
Right, Mosaic. It stands for Breaking the Optics versus Copper Trade-off with a Wide and Slow Architecture and Micro-OLEDs. Quite a mouthful, but descriptive.
So our mission today: unpack this thing. What makes it tick? What are the materials, the design choices, and maybe most importantly, what could this mean for scaling networks, GPUs, and maybe even entirely new ways of building computers?
Well, the fascinating thing about Mosaic, like you said, is not just a small step forward. It feels more like a complete rethink. The papers claim some pretty amazing numbers.
Like what?
A 10-fold increase in reach over copper, so up to 50 meters. That's huge.
Yeah.
And at the same time, up to 68% less power, and it's supposedly 100 times more reliable than the optical links we use now.
Okay, that sounds almost too good to be true, Ho.
So the key idea, the sort of secret sauce, is throwing out the old playbook. They ditch what's called the narrow and fast model, just a few really high-speed channels.
Right.
Instead, Mosaic goes for wide and slow. Hundreds of parallel channels, each running much slower. It's this shift that lets them, well, kind of sidestep the physics that penalizes high-speed links so badly.
Okay, let's dig into that curse of narrow and fast, because this is what everyone building AI stuff is grappling with right now. You mentioned the trade-off triangle. Let's look at the current options.
Yep.
So first, you've got copper links, electrical cables. People like them because, well, they're cheap and super reliable.
Very reliable. Yeah.
But the killer is reach. You said less than 2 meters.
Typically, yeah, for the high speeds we need today. And it gets worse. The faster you go, the shorter the reach. That next-gen 1.6 terabit stuff,
Yeah.
they're expecting maybe less than a meter for copper.
So basically, copper keeps everything crammed inside one single rack.
Exactly. It forces this incredibly dense, potentially very hot configuration. There are physics reasons for this, too. It's not arbitrary.
Go on.
Oh, it's mainly two effects that get exponentially worse with speed in copper. One is the skin effect. The signal kind of travels only on the surface of the wire at high frequencies, which increases resistance. And the other is dielectric loss. The insulation around the wire starts absorbing signal energy. Both basically eat the signal alive, so you have to keep shortening the cable just to get anything through.
Okay, so that's copper. Reliable, low power, but basically zero reach. What's the alternative?
The alternative is traditional optical links. Usually these come as active optical cables, or AOCs. They solve the reach problem instantly. Tens of meters, easy. You can connect racks, rows, no problem.
But there's always a but.
A big but. Two big buts, actually. First, they suck down power, a lot of power. And second, their failure rates are, frankly, terrible. The sources say up to 100 times worse than copper.
100 times. Wow. So why does relying on narrow and fast cause these issues, both in copper and optics? Let's fake an 800 gig link, maybe 8 channels running at 100 gig each. Why is that specific approach the problem?
For optics, it's all about the complexity needed to handle that speed. You need really sophisticated electronics. Okay, so first, you need fast laser drivers, modulators, to actually create the light signal. Then, you need very fast converters, analog to digital, digital to analog ADCs, and DACs. And here's the real power hog. You need a ton of digital signal processing, DSP, and forward error correction, FEC.
Why so much processing?
Because at those high speeds, the signal gets messy. You get noise, jitter, crosstalk, all sorts of problems. The DSP is constantly working, filtering, trying to clean up that signal, and the FEC adds extra data bits so the receiver can hopefully fix errors that inevitably creep in.
Ah, so it's like shouting louder and adding error correction codes because the line is noisy.
That's a decent analogy, yeah. And all that digital logic running on the fastest, most expensive silicon, it burns watts, several watts, just for the processing on each end of the link.
And I guess that complexity doesn't help reliability either.
It directly hurts it. Pushing those speeds stresses the active parts, the lasers, the modulators. They're delicate, sensitive to heat, voltage changes. Running them flat out generates heat, makes them age faster.
Mm.
And when the signal quality is already marginal because you're pushing the speed limit, even tiny changes, a bit of heat, a component aging slightly can cause the link to fail. That's why you see those really poor FIT rates, failure and time rates for traditional optics.
We don't even need hypotheticals here. The sources point to the NVIDIA NVL72 pod, that massive system with 72 GPUs all linked together.
Right, a prime example.
They had to pick an interconnect for those crucial links. The research we saw suggests if they'd gone with standard optics, the power cost would have been insane, something like 20 kilowatts extra per rack.
Yeah, that's the estimate. Think about it. A high-end GPU is maybe 1 kilowatt. So 20 kilowatt is like sacrificing 20 GPUs worth of power just for the network inside the rack. It was just too much.
And the reliability.
That too. Imagine a 100,000 GPU cluster. With typical optical link failure rates, you'd expect a link to die every, 6 to 12 hours? For an AI training job, that might run for weeks.
Catastrophic.
Totally. Every failure means stopping, saving everything, fixing it, restarting. Just huge amounts of wasted time and money.
So for the NVL72, they went with copper, solved power and reliability, but then, bam, the reach problem.
Exactly. All 72 GPUs had to be jammed into a single rack because copper can't go further.
Which created its own nightmare, 120 kilowatts in one box.
Right. Which then forces you into really complex, expensive liquid cooling. And the sources suggest that complexity was a big reason for deployment delays. It just perfectly illustrates this inescapable NAF trade-off. You're damned if you do, damned if you don't.
Okay, so if narrow and fast is the disease, Mosaic claims wide and slow, or WAS, is the cure. That's simple, more lanes, slower speeds. Why haven't we done this before in networking?
Well, the concept isn't totally new. We've seen similar shifts inside chips, right? Chip-to-chip links, memory buses like UCI, or a bunch of wires.
Right, they went parallel and slow for better power efficiency.
Exactly. Better PJ bit, picojoules per bit. Mosaic is basically taking that same idea and applying it outside the chip at the rack or even row level.
So how does it work in practice, that 800 gig link example?
Instead of, say, 8 lanes at 100 GBPs, Mosaic uses a lot more lanes. The paper talks about a 20 by 20 array of emitters. That's 400 parallel channels.
400.
400, and each one is just cruising along at a relatively relaxed 2 gigabits per second using simple on-off keying.
Okay, so why couldn't we do this before? You mentioned two reasons. Copper first.
With copper, if you try to pack hundreds of wires that close together, you get massive electromagnetic interference, EMI, and crosstalk. The signals just bleed all over each other, becomes unusable almost immediately.
And optics. Why not just use 400 standard lasers?
Power and heat. Your standard communication lasers like VCSELs or DFBs, they burn tens, maybe hundreds of milliwatts each. Multiply that by 400.
Whoa, okay. That's like 40 to 80 watts just for the lasers themselves.
Yeah, you'd melt the transceiver module. Plus, imagine trying to manufacture, align, and package 400 individual lasers accurately. The cost and complexity would be astronomical.
So Mosaic needed a different light source and the WAS architecture. The combination unlocks that magic triangle: reach, power, reliability.
That's the idea. Let's tick through the benefits again.
Okay, reach. It's optical, so no skin effect problems. They're getting up to 50 meters. Way better than copper.
Check. More than 10x the reach of high-speed copper.
Power efficiency. Because they ditched the high-speed electronics, the DSP, the fast ADCs, they claim up to 68% power savings over NAF optics.
Right. Huge savings there.
And reliability. This seems key. With 400 channels, losing one isn't a big deal.
Exactly. Redundancy becomes almost free. If you have 8 channels and lose one, that's a big chunk of bandwidth gone. Lose 1 out of 400. Who cares? This inherent redundancy, plus a more robust light source we'll get to, boosts reliability by, they claim, 2 orders of magnitude, back to copper levels of reliability.
That sounds like the holy grail for these big AI systems, but what's the catch? Is it slower overall? Does WAS sacrifice anything?
Well, yes, the individual channel speed is much lower, obviously, 2 GBPs versus 100 GBPs, but the aggregate bandwidth is still high, 800 GBPs, 1.6 TBps. So for the network, that trade-off seems perfectly fine.
And can it scale up? What about 1.6 terabits or 3.2?
It seems straightforward. The sources say they can scale just by adding more channels, maybe go to an 800-channel array, or they could nudge the per-channel speed up slightly, maybe to 4 or 8 GBPs per lane. The power efficiency still holds up well, even at those slightly higher speeds.
And critically, does it plug into existing gear?
That's a huge point, yes. It's designed to be protocol agnostic, doesn't care if it's PCIe or Ethernet running over it, and it fits into standard QSFP or OSFP module slots. So Potentially a drop-in replacement. No need to rip out and replace entire servers or switches.
Okay, this wide and slow thing sounds great, but it all hinges on that light source. You can't use normal lasers, so what are they using?
This is where the material science gets really interesting. They're using micro-LEDs.
Like the things in fancy TVs.
Sort of, but think much, much smaller and optimized for communication. Specifically, the ones Mosaic uses for blue and green light are made from gallium nitride, or GaN.
GaN. I've heard of that for power electronics.
Right, it's a very robust material. Using GoLin lets them emit light in the visible spectrum 400 to 700 nanometers. This is totally different from standard telecom lasers that use infrared light,
Yeah.
like 850 or 1550 nanometers.
And they're tiny.
Incredibly tiny, just a few micrometers across, maybe tens of micrometers at most, and because they're so small, they sip power. We're talking hundreds of microwatts per LED.
Microwatts compared to milliwatts for lasers.
Exactly. Orders of magnitude less power. That's the key that allows them to pack 400 emitters into a tiny module without a meltdown.
Okay, lower power is huge, but why are they inherently more reliable than lasers?
It comes down to how they make light. Lasers use stimulated emission. They need complex structures, mirrors, cavities to get the light waves lined up and amplified. That makes them precise, but also finicky sensitive to heat voltage spikes.
Right.
Micro-LEDs use spontaneous emission. They basically just glow when you put current through them, like a tiny light bulb. Much simpler physics.
So no complex threshold to maintain.
Nope. That means simpler manufacturing, likely lower cost, and critically, they're just fundamentally more robust, less sensitive to temperature changes. This is a big part of that claimed 100x reliability improvement over laser-based AOCs. They're using materials like gallium nitride instead of the more complex indium phosphide or gallium arsenide used in many telecom lasers.
Okay, but using a tiny light bulb for datacomms, surely it's not perfect. You mentioned drawbacks.
Right. Two main challenges they had to engineer around. First, Lambertian emission,
Meaning
it emits light everywhere in a wide hemisphere, not a focused beam like a laser. If you just stick that next to a tiny fiber core, most of the light misses. And in a dense array, that stray light causes crosstalk between channels.
Okay, so messy light. What's the second problem?
Broad spectrum. The light isn't one pure color. It's spread out over maybe 10 nanometers or more. Over distance in a fiber, different colors travel at slightly different speeds. That's chromatic dispersion. It smears out the signal, which is bad even for a simple 2 GBP's on-NO off-F signal.
And trying to manage 400 individual fibers sounds like a nightmare, too.
Absolutely impossible in a small connector. So they needed a different kind of fiber.
What do they use?
They borrowed tech from medical imaging, actually. Multi-core imaging fiber. These are fibers that already contain thousands, maybe up to 10,000 tiny individual cores bundled within a single outer jacket.
So one cable carries all 400 channels.
Exactly. It massively simplifies the cabling and connector side of things. No more unwieldy bundles of 400 separate fibers.
But aligning 400 tiny LEDs to 400 tiny cores still sounds hard and expensive.
It would be, except they have a clever trick. Since there are so many cores available in the imaging fiber, they don't need perfect one-to-one alignment. They map each micro-LED to shine into a small group of fiber cores.
So it just needs to hit the target area, not the exact bullseye.
Precisely. It relaxes the alignment tolerance dramatically, which is critical for keeping manufacturing costs down.
Okay, that handles the packaging. What about the messy Lambertian light? How do they focus it?
They developed custom micro-optics. Specifically, a total internal reflection TIR lens system. Think of it like a miniature high-tech reflector dish for each LED.
TIR, like in fiber optics.
Same principle. They designed a special two-part microlens that captures that wide-angle light and uses internal reflection to collimate it to narrow it down into a much tighter cone.
How much tighter?
The numbers are impressive. They went from light spraying out over 180 degrees down to a focus cone of about plus or minus 12 degrees. They claimed this boosted the light coupling efficiency into the fiber by more than double, compared to standard off-the-shelf microlenses.
And can they make these tiny custom lenses cheaply?
That's key, yes. The design is compatible with wafer-scale manufacturing techniques like nanoimprinting. It's not just a lab prototype. It's designed for low-cost, high-volume production.
Okay, so that's the transmit side. What about receiving the visible light?
This is another big win for simplicity. Because it's visible light, they can use standard CMOS sensors. Basically, the same silicon photodetector technology that's in your phone camera.
So they tap into that huge, mature, low-cost silicon ecosystem.
Exactly. No need for expensive, specialized infrared detectors made from exotic materials like indium gallium arsenide that you need for standard telecom wavelengths.
And does using CMOS help with integration?
Tremendously. The CMOS sensor technology is the same as the rest of the receiver chips, the amplifiers, the basic logic. This allows for monolithic integration.
Meaning,
They can put the photodetector array and the initial amplifier circuits all on the same piece of silicon. Fewer separate chips, shorter electrical paths between them, which means lower cost and, crucially, lower power consumption because you minimize those parasitic capacitances.
let's really nail down the power savings then. You mentioned the comparison figures. They seem pretty dramatic.
They really are. Let's look at the breakdown the research provides. An 800 gig NAF optical module, the current standard might pull somewhere between, say, 9.8 and 12 watts at one end.
Okay. And where does that power go?
A big chunk, maybe 3.5 watts, goes to that digital backend, the DAP, the CDR, the ADC stakes. Another big chunk, maybe 4.7 watts, goes to the analog front end and the lasers themselves.
Now compare that to Mosaic at 800 gig.
Total power drops to between 3.1 and 5.3 watts per end. That's a 56% to 68% reduction overall. But look where the savings come from. The digital backend power plummets to just 0.4 watts.
Wow.
And the analog side, including the micro-OLEDs, drops to around 1.2 watts. It's clear that shedding all that complex high-speed digital processing is where the massive win comes from.
That's huge for OpEx, the electricity bill for a data center. What about the cost to buy the modules, the CapEx?
That's another potential advantage. Because Mosaic doesn't need that heavy DSP or those ultra-fast converters, the chips likely don't need to be made on the absolute cutting-edge, most expensive silicon process nodes like 5 nanometer, 7 nanometer.
They could use older, cheaper manufacturing processes.
Potentially, yes. Using a more mature, larger process node could significantly lower the manufacturing cost of the electronics, adding a CapEx saving on top of the OpEx saving. It's a compelling economic argument.
It really feels like the simplicity enabled by WAS is the core strength here.
I think so. Take the data encoding. Because each channel is only running at 2 Gbps, they can use the simplest possible scheme, NRZ. Just on-off F.
No need for complex PAM4 signaling.
Exactly. PAM4 has 4 signal levels, it's much more sensitive to noise, and it absolutely requires those power-hungry DACs, ADCs, and strong FEC to... Massive. No complex DSP. The sources say they only need some simple analog equalization to clean up minor signal issues, and they have another really clever trick thanks to WAS clock forwarding.
What's that?
In a normal high-speed link, the receiver needs a complex circuit called a clock and data recovery unit, or CDR. It has to extract the timing information from the incoming noisy data stream. CDRs burn significant power. With Mosaic, they have hundreds of channels. Channels are cheap, so they just dedicate one channel purely to sending the clock signal directly from the transmitter to the receiver.
Huh. So the receiver doesn't have to figure out the timing, it's just handed to it.
Precisely. It completely eliminates the need for the power-hungry CDR circuit. Huge power and silicon area savings. Trying that in an 8-lane nav system would waste 12.5% of your bandwidth on the clock, but in a 400-lane system, it's a negligible 0.25% overhead. It's only practical because of the WAS architecture.
And this idea of cheap channels feeds right back into reliability, doesn't it?
Absolutely. Redundancy is affordable. Mosaic uses a two-pronged approach for fault tolerance.
Layer 1.
A lightweight error correction code, like Hamming code, running across groups of data channels. This can instantly correct, or at least detect and locate, a single-channel failure without interrupting data flow.
And layer 2.
Hot spares. They include a few extra unused channels. When the ECC detects a channel has permanently failed, the system quickly reroutes that channel's data onto one of the waiting spares, near zero downtime.
How much does this improve the numbers? You mentioned FIT rates.
Yeah, failure in time, 1 failure per billion hours. High-speed optics can be in the hundreds of FPs, which is pretty bad at scale. Mosaic simulations show that adding just 5% spare channels pushes their FIT rate down below 20.
Below 20?
That's an order of magnitude better than typical optics. And critically, it puts Mosaic in the same ballpark as ultra-reliable electrical copper cables. So you potentially get the reach of optics with the reliability of copper. That's the promise.
Okay, so better reach, lower power, copper-like reliability. Historically, breakthroughs like this in networking tend to unlock completely new ways of building computer systems.
For sure. Better networks always change the architecture.
So what could Mosaic enable? Let's start with the network itself, that 50-meter reach. What does that change?
Well, for one thing, it could let data center operators get rid of the top-of-rack switch, the TOR.
Why is that good?
TORs add latency. They're another point of failure, and they consume power. With 50-meter reach, Servers could connect directly to larger switches at the end of the row, or maybe even aggregation switches further away. It simplifies the network physically.
And makes different network shapes possible.
Exactly. Those really high-performance topologies you hear about for AI, like multidimensional torus networks or dragonfly or hypercubes, they often need connections that are longer than what cheap copper allows. Mosaic makes building those much more practical and affordable compared to using today's power-hungry long-reach optics.
Interesting. What about inside the server, or maybe even inside the AI accelerator itself? You mentioned GPU disaggregation.
Yeah, this is where it gets really intriguing. Think about today's monster GPUs. They're huge chips, often multiple smaller chiplets stitched together on a complex, expensive silicon base that CoWoS technology from TSMC.
Right, chip on wafer on substrate. It's become a bottleneck, hasn't
A
it?
huge bottleneck. It's complex, expensive, limits yield, and TSMC can't make enough of it. Mosaic offers a potential way around that. Instead of building one giant, complex, multi-chip package, maybe you build smaller, simpler, single-die light GPUs, easier and cheaper to manufacture, and then you connect them together using a Mosaic-like optical fabric.
So the connections move off the silicon interposer and onto an optical network between these smaller GPUs.
Potentially, yes. You'd replace those millimeter-scale electrical CoWoS links with maybe centimeter or meter-scale optical links enabled by Micro-OLEDs. It shifts the integration challenge from the super difficult chip manufacturing step to a potentially more manageable optical assembly step.
Okay, that's GPUs. But you also mentioned the holy grail, memory disaggregation.
Yes. This, I think, is where wide and slow could have its biggest impact on compute.
People have talked about separating memory from compute for years, right? Let you scale them independently.
Exactly. Especially for GPUs, which are hitting limits on how much high bandwidth memory, HBM, they can physically stack onto the package. HBM is amazing, but it's incredibly expensive and capacity limited.
So why hasn't memory disaggregation taken off?
Latency. Simple as that. Memory access needs to be fast. Even a tiny delay stalls the processor. Traditional optical links, the NAF kind, were just too slow.
Why slow? They have high bandwidth.
High bandwidth, yes, but high latency. Remember all that DSP and FEC they need to clean up the noisy high-speed signal? That processing takes time, maybe 50 to 100 nanoseconds added latency just for the link electronics.
And that's a killer for memory access.
Absolutely. It could easily double or triple the time it takes to get data compared to on-package HBM. Makes the whole idea pointless.
So how does Mosaic fix this?
Because Mosaic runs slow on each channel, it doesn't need the heavy FEC or complex DSP. The latency added by the link electronics themselves is minimal, maybe just a few nanoseconds. It's fundamentally a lower latency path.
A few nanoseconds. That's close enough to HBM speeds to be useful.
It's getting into the realm where it becomes really interesting. It makes off-package memory, maybe pools of cheaper DDR memory, shared across multiple GPUs via an optical link, a much more viable prospect. This could break the HBM bottleneck, give GPUs access to vastly more memory, which is crucial for things like running massive AI inference models.
And thinking longer term, does this tech, these GaN micro-LEDs and CMOS detectors, have implications beyond just data links? You mentioned photonic computing.
Well, it's definitely a step in that direction. While Mosaic is focused on electrical-optical conversion for links between chips or servers, the core components, tiny, low-power, mass-producible optical emitters and detectors integrated close to silicon logic, are exactly what you need for more advanced concepts.
Like optical I/O right on the processor package.
Yeah, co-packaged optics, or eventually, maybe even replacing some electrical wires inside the chip with light for higher bandwidth density and lower power.
Being able to make hundreds or thousands of these optical components reliably and cheaply using CMOS-compatible processes, that's a fundamental building block you need to even think about practical photonic computing. Mosaic helps build that foundation.
So zooming back out, the big picture is longer reach, low cost, high reliability could lead to much bigger, more flexible AI clusters.
Yes, larger training domains, less fragmentation. And maybe it enables a truer form of elastic computing.
What do you mean by that?
If you can connect resources, compute cores, memory banks, accelerators over tens of meters with low latency and low power, maybe you can dynamically assemble the exact hardware configuration a specific workload needs, right when it needs it. Pull together resources from across racks into a temporary optimized virtual system. That kind of flexibility could drive huge efficiency gains.
Okay, let's try to wrap this up. Mosaic seems like a genuinely different way of thinking about network links. I'd agree. It's taking the best bits of copper, the low power, the high reliability, and combining them with the reach of optics. And it does this by flipping the architecture to wide and slow, using these efficient micro-LEDs on gallium nitride, coupling them with imaging fiber and some clever custom optics.
And it's designed to be practical, backward compatible with current standards.
Which is crucial for adoption, yeah. It offers an immediate path to scale current networks better. But I think its real potential, the exciting part, is enabling those future architectures, disaggregated memory, maybe disaggregated GPUs, things that the old narrow and fast approach fundamentally couldn't support because of power or latency issues.
So if these kinds of low latency, high bandwidth optical links become common, maybe even reaching inside the server chassis or onto the processor package,
Hmm.
what's next? What's the next big thing in the server that gets pulled apart and reconnected optically? Maybe the storage network
Yeah.
or connections between CPU cores themselves. That's something to think about.